Hello, this is Dr. Liu, and in this video I will review chapter 18, question 8, 9, and 13. These are all just matrix method looking for the system matrix, and you'll be hand sketching some object-image relationships, but you're not going to calculate an image out of an object. So these are all grouped together for this reason. So let's start with 18.8. 18.8, we have a lens that has the following specification. So 8, we have radius R1 equals 1.5, and that's equal to R2 as well, and the thickness is equal to 2, and index refraction is equal to 1.0, another index refraction is equal to 1.6, and the third index refraction is 1.3. So the goal is to find the principal points using the matrix method, include a sketch roughly to scale, and do a re-diagram to find a finite object of your choice. Find basically to retrace an object. Okay, so the radius curvature here, if you look at these, it just means both sides are 1.5 positive, right? So they're both 1.5 positive. It's not a double convex. It's one side is convex, the other side is concave. So it looks like this. Some thickness. If it's okay, it looks like this. And this is the front side, that's the back side. So I'll go through some details since this is the first question to review. So we have here a refractive operation happening here, and here we have some sort of translation, and here is some refraction again. So the system matrix should be the combination in the right order. Refraction, and then translation, and then refraction again. So first multiply these two, then multiply that. Okay, so for refraction matrix, we're looking at, hopefully that's enough space. So let me go and grab that formula there. So for refraction matrix, 1 over R, this is RL over RR, or the prime on the right, minus 1, and then the left side over the right side. Okay, so that makes R1 equal to, here's 1, so the left side, right side, that's N1, here's N2, here's N3, so different media on this side. And this might be, I don't know, maybe water, this size air. So 0 and 1 over 1.5, that's a radius. So left side over right side, minus 1. Then left side over right side. Okay, so we can do a calculation here, but I'll use Python because this is already given you what it is. You don't really have to, I don't have to hand calculate that, so I'll leave that, and I'll do a T1. The T is easy. We just have a 1. There's a length. Here's actually I should have written T here. Let's do that. T is equal to 1 L 0 1. Okay, so this T1, we'll just remove that and put a 2 centimeter here, 0 1, and then R2, just be careful here which one's left, which one's right. And the radius curvature is still 1.5, and the left over right, left is N2, so it's 1.6, the right is 1.3 minus 1, and the left is 1.6, right is 1.3. So maybe write the numbers down. This is 1, 1.6, 1.3, so you can refer to them on your diagram. So we'll calculate that, and then our system matrix. Let's do that in steps. So I'll first calculate T1 times R1, which is I'll get these two first, right? So this is a good time to look at the program that I posted. Let's move that out. So this is the program I posted. There's a lot of lines here, I'm sure, but they're all just replicating. Okay, let's do 12 point. So okay, just replicating different questions. So this is kind of a service routine, things that we need to get different elements out, and then the rest are just problem solutions. This is a generic problem, don't worry about that, and that's an example problem, and then this starting here, question number 1, 3, 4 in order. So if you look at question number 8, this is question number 8. So first I got a refractive matrix like this, and then I get translation matrix, and I get that. So here's what I do. I run this program and just run the module. Okay, so it's running the import of a symbolic pi. Okay, this says chapter 18, select problems, and these are questions, just cardinal points. So see a solution, type something like this. So we'll do HW8. The thing about this is now we have everything, and we can also try the refractive surface. For example, get R. So we'll need the radius of curvature in the refraction. So that is the R1 I was trying to calculate. Now I can actually just get it, and that is I can do a quick proof to calculate that. Just let's see. Okay, so I was doing that. Let's just calculate the bottom left component here. So 1 over 1.5, I'm based off this expression here, times 1 over 1.6 minus 1. Okay, so that turns out to be just the right number. So okay, that makes it make us feel better that this calculation is right. So we'll copy it over here. So it's a 1, 0, negative 0.25, and positive 0.625. Okay. And we can also calculate R2. R2 is that, and I can do just to get that same radius of curvature. Left is 1.6, right is 1.3. So I can get a refractive surface just like that. Okay, so well, less elegant looking, but that's all dependent on the values. So here's 1, 0.154, 0.154. I will keep 3 sig figs. 0, 1.23, 1.23. So that's our R2. So let's do some calculations here. T1, R1. So I'll demonstrate how to do that. And this is 1, 2, 0, 1 times R1, which is 1, 0 minus 0.25 and 0.625. So let's skip the leading 0 to save some space. Okay. Okay, I've done this before in separate videos. So first row, this first row, first column should be from the first row of the first one, and then first column that second one. Okay, so first row, that's 1, 2 multiplied by that. So it's 1 times 1. So this and 2 times negative 0.25. Okay, so that's first row, first column. First row, second column. So that 1 minus times 0, then 2 times this, 2 times 0.625. And then second row, first column, that gets you second row, first column. So that times that, 0 times 1 plus 1 times negative 0.25. And then second row, second column gets you the second row, second column result. So that is 0 and 0, 0 times 0 plus 1 and 1 times 0.625. So we have this intermediate answer, that's a 1, 2 and a quarter times a quarter is a negative half. So you have positive half, and it's a 0, so twice 0.625, so that could be 1.25, and then 0, that's a 0, this is minus 0.25, and here's a 0 again, this is 0.625. We can check our calculation with Python. That's called R1 equals get R 1.5, 1, 1.6. These are the indices fraction. R2 will get that equal to 1.5 centimeters, 1.6 index refraction, 1.3 on the right side, and T1 equals I just get T, I just need a distance of 2 centimeters thick. Okay, so I can do T1 R1. Okay, and everything checks out, so my calculation so far is correct. And then the next step is the R2 times this T1 R1. So R2 is this 0.154, 1.23, then times 0.5, 1.25, minus 0.25, 0.625. Okay, so we'll do this more quickly now. That times that, that's only a half. Then that times that, that's 1.25. And this times this, okay, it's a little more difficult now, and we'll use Python instead. And this times that, that's also difficult, so I think it's best if we just use Python. And okay, take a sneak peek. This is the A, the B, the C here is this negative 0.231, and this spot is D, so 0.961. I can calculate just like this, so I can do R2 times T1 times R1. Okay, so that should get us the same thing. Okay, so now that we have the system matrix, we can find out all of the variables. For example, the PQRS, VW, and F1, F2. So we can do P equals, we have a list of these formulas. Let's say, let's move that to the left. I'll put a page number, page 404. You'll find all these matrices, and then with the PQRS, I'm going to point you to a list that's on page 410. So page 410, you'll find these formulas. So P is D over C. Okay, let me just write over this. Let me see if I can get a I don't really have a marker here or highlighter. So this is A, this is B, this is C, this is D. So D over C is this over that. It's going to be 0.961 over negative 0.231. So a little over negative 3, and we got negative 4. Actually, yeah, negative 4. So negative 4.17. So then you can keep going with page 410's formulas, all of these formulas, and the Q is equal to negative A over C, so that gets you negative A. So A over C, so the negative cancel the negative, you get 0.5 over 0.231, so that's roughly a 2, a little over a 2, so 2.17. And you can keep going. I have the list right here. I think it's pointless to go through all the algebra. And what I want to point out is, in my previous version of the matrix manipulation, I did not put in the n left and n right into my formula. I only assumed they're going to be always the same, left and right. But now I have put them in. Let's see. So if I scroll to the top, so now I have n1 over n2, nl over nr, excuse me, is defined as AD minus BC. This is the determinant of a matrix. The determinant of the matrix is always the very left medium over the very right medium. We talked about it. This is because the refraction matrix has that as its determinant, and all the other matrices, their determinants are equal to 1. So if you multiply them all together to get your system matrix, the system matrix will have its determinant equal to n left over n right. So that's how I got the n1 over l over nr. So I included that in all these calculations where they appear on page 410. I probably could put in a reference here as read page 410, something like this. So everything from Pajodi, page 410. Okay, so back to the reading up notes. Okay, so now you have the system, and with all the parameters all here, and the rest it just wants you to draw something and that makes something that makes sense, and then do an object image relationship with it. Okay, so we can certainly do that. We have I think we need those numbers, but I can move to it doesn't really want me to move to the left anymore. This program, it's got its issues. Okay, so I have this object here, this thing. I'll redraw it. So here's the 2 centimeters. Okay, good. So let's see what we need. So PQs are measured from the input plane to the focal point, so we can certainly use that. Negative, it means pointing to the left, so 4.14. So if the thickness is 2, so then from here about here, this is F1. And then Q is from here is positive, so it points to the right. So from the output plane, about 2. So that's a little over 2. So here it is, F2. Okay, I have gotten these 2 points, and RS are pointing from the input plane and output plane to the principal point. So R is minus 0.83. So it's from here to the left. So 0.83. Here's each block is a 2. This half of that is 1. So I may as well just put a point right here. So this is H1, and S is negative. That means S is also to the left of the output plane, and S is negative 2. So that's skipped over here and shows up here. Okay, that's H2, and then V and the W, and apparently V and W are not the same as RS. I can put that in there, but unless I use that nodal rate, I don't really have to. Let's see where V is. V is 0.1617. So V is measured from here to the nodal plane. So inside here's nodal plane 1, nodal point 1, V actually N 1, and the W is minus 1.16. That's measured from the alpha plane to the left. So half, a little more than half, so that's N2. Okay, and the focal length already given. So how do I make an image? I would rather do a real object, real image. So here I have focal point 1. I'm just going to draw something over here. So that's my object. I'm going to use a different color. Okay, so try to do all of these reads. So first read, that is going through the focal point. So okay, going through the focal point, not too good. Okay, I drew it pretty long. So what I want to do is go into the focal point, and it'll okay, it'll keep going until it gets to the first principal plane, which is here. So it stops going like that. It starts to go horizontally out. Yeah, I know it's missed the whole optics, but that's not the point here. This is retracing, trying to create an image. So okay, that's parallel. And then the second one, the second ray could be a ray that is going horizontal, and then it hits the second nodal point and start bending towards the second focal point. So here's the second, not nodal point, excuse me, principal plane. So going horizontal and it here, it starts going through that. So let's see. If I have a ruler, I'll use a ruler. Okay, I'll use this ruler. I missed it, but that's okay. So here is the image, and that's roughly. So I bet if I place this a little further away, I'll get a slightly more minified image. It's a little easier to handle. Just don't put it within the first within the focal length. Then you have to do a virtual image, making it a bit more difficult. Okay, so that is question number 8. So we also have 9 and 13. So let's get those started. Okay, so question number 9, we have a positive thin lens of focal length 10 centimeters is separated by 5 centimeters from a thin negative lens of focal length negative 10 centimeters. So we have two lenses and they're 5 centimeters apart. Find the equivalent focal length of the combination and the position of the foci and principal planes using the matrix method, matrix approach. Show them in the sketch of the optical system roughly to scale and use them to find the image of an arbitrary object placed in front of the system. Okay, so this is again looking for cardinal points and not necessarily getting an exact image out of an exact object. So that's the same exact thing here, except that different elements are used, and this time we're using thin lens and also translation. So I may as well just add a thin lens here. So a thin lens, let's see what I use for thin lens. I probably use L. 1, 0, here's a 1, minus 1 over F. So that should be thin lens. Also should be on page 404. Let's just make sure that's in there. So page 404 has all these things. So our system should have one thin lens and the translation, that's the length 5 centimeters, another thin lens, and just to indicate the order of operation, that's the order. And let's get the thin lens. So L1, the focal length is 10. So 1, 0, minus 1/10, and 1. And T1 is 5 centimeter of translation, so T1 is equal to 0 is 11501. And then L2 is another length with negative 10 centimeters. So 1 over the negative 1 over the focal length, that's equal to 110. So 0, 1. And you just multiply them all together in the correct sequence. So T1 first left multiply the L1. So you have T1 L1, that's equal to something. And then you have the L2 times the T1 L1, that is equal to the something else. That's the system matrix. Alright, so I'll just write it out by running my Python code. I think I demonstrated in detail how to do matrix manipulation in the previous question and a separate video. So I'll skip that. So the system matrix, let's go to this question here. Okay, I already ran this program. That means it has all of the solutions loaded. You just have to print it. So this is question 9 here. So do question 9. That looks pretty similar. You have two lenses. You have a distance. So one lens, a distance, another lens, and then it gets you the cardinal points. So let's run homework number 9. Okay, so that's all printed out. We have the A, B, C, D here. So we have, I probably should print that as a matrix anyway. So half, then 5. And then C is minus 0.05, D is 1.5, minus 0.05, and 1.5. And then to calculate PQRS, VW, you go for the same set of equations on page 410. I'll calculate a couple of them. So P is equal to D over C. So D over C, so that's negative 1.5 over 0.05. So negative 30, I think. Yep. And Q is equal to, according to our formula, we have calculated only PQ, negative A over C. That's negative, that's A, that's C, so that over that is 10. Negative 10 is positive 10. And then we can calculate the rest. This one has all of those already. And then we're supposed to be creating some diagrams, some drawings. Okay, so we'll create some drawings. We have some space. We have two lenses. So here's one lens. So 5 centimeters. How about let's have 2 of these. Okay, each block is 2.5 centimeters. Alright, so let's read the result from here. So first P is 30 centimeters. That's 6 times 2 is 12. Basically, it's quite a way away. Maybe I can move that down. Maybe like that. Okay. The center line. Okay, so that's 1, 2, 3. Oh, oops, missed. 1, 2, 3, 4, 5, 6. This is over here. This is F1. And Q is 10. So that's measured from this side going 10. That's 2.5, 5, 7.5, 7, and 10 right here. F2. And R would be from here minus 10 is that. Wait, actually this is 5. Sorry, 5 is minus 10 is here. So this is the first principal plane. This one also was wrong. That It's only this far, F2. And S is -10. That means the second principal plane is to the left of the first of the exit plane. So 5 and 10 here is H2. Okay, strange. And then PQRS, V is -10. So -10 is here. So H1 also N1 because the media are the same on both sides. And then W is -10. So from here, -5, -10 this is also N2. Okay, so now we have this. We should be able to draw some retracing. And again, let's set up something that's a bit further away. So maybe I can set something up like this. Okay, so how do we draw this? So first of all, we can go through the focal point and then hit the first principal plane, and then bend suddenly into a horizontal ray. And in doing this, I need a longer ruler. Let me see what I can find. Okay, got a longer ruler. Okay. It's here. It's here and it becomes horizontal. Okay, good enough. And then the second ray is horizontal and it hits the second principal plane and becomes focused. So the second line is just this grid line because that is where I drew the object. Right here is here, and then goes through that, the second focal point right here. Okay, so this is your image. So it's just an arbitrary image, and sorry the numbers are kind of big, but that's what this is. If you think about this, it's okay. I think I forgot to do one last thing. Is the finding the effective. Let's see what it says. Equivalent focal length of the combination. Okay, so F1 and F2 are the same. It's, if I remember right, this is 1 over C. So 1 over C, I'm looking for, let's do absolute value of these because we just want the effective, right? So that is here, 20. So 20 centimeters. So these two, let's make sure it's right. Yep. Okay, it's right. So equivalent is 20. Alright, so one last question before this video gets too long. Let's back up. So question number 13. Alright, 13, we have a thick lens. It presents two concave surfaces, each of radius 5 centimeters to incident light. The lens is 1 centimeter thick and has a refractive index of 1.5. So we want to find the system matrix, and then we want to do a retrace. A matrix and also terminal points, and then retrace. So in question 13, I took a look at the solution. So what the solution says here is, okay, the 13, we have 0.5 and -0.5. So let's see, two concave surfaces. So essentially the see what the solution here has. Give me a second. Okay, negative. Okay, so Alright. So that's what they're going for. And we have the index of refraction equal to 1.5. And the radius of curvature is 5 centimeters. Okay, they're both negatives. So R1, which is the left one here, will have 1, 0. This is actually related to the R here. 1 over R, left over right, minus 1. So 1 over R, so this is going to be in the denominator minus 5. And then left over right, 1 minus 1.5 minus 1. And then left over right, 1 over 1.5 over to the right. Okay, so that's the first refractive surface. I'm just checking to make sure it's right. Yep. Okay, so then the translation, I forgot to write the thickness down. The thickness is 1 centimeter thick. So this translation is a 1 centimeter 0 1. That's a pretty simple matrix. And then the second refraction, that's basically the same overall. So 1 0 1 over minus 5, again a concave surface, 2 concave surface. It's not a double concave, it just has 2 concave surfaces. And then the left is 1.5, right is 1, minus 1. Left is 1.5, or right is 1. So that's the refractive surface 2. And the system matrix is refractive surface 1, translation 1, and then the result, refractive surface 2. So let's go to Python this time just to calculate, since we have done so many times just with that. So this is question 13, so do 13, and here's our system matrix, so A, B, C, D, and top left, top right, bottom left, bottom right. So then the PQRS are these. So do you want to draw another retracing? Of course you can draw another retracing. So the thickness is 1 centimeter, just have that in mind. And PQ are pretty large, so you probably want to just draw this as a pretty thin line. And then RS and VW. So let's see what is the best way to draw this thing. So if this is maybe a 1 centimeter thickness, so P is minus 140 to the left, Q is 160 to the right. So okay, 1 2 3 4 5 6 7 8 9 10 11 12 13 14. So if I count the blocks roughly here, I'm not counting the 1 centimeter thickness, and then I do 1 2 3 4 5 6 7 8 9 10 12 14 16. So is that right? 160. Yep. So that's F1, that's F2, and then we can look at RS. R is to the right side, 10 centimeters. So from this to the right, that is where the first principal plane is 10, and also S is also 10, but that's not overlapping with R because they're actually 1 centimeter apart. R is from the left surface to the right, S is from the right surface to the right. They're both 10 centimeters to the right, but they're from different sides of surface. So 1 2 3 4 5 6 7 8 9 10. So I will draw this is the R that gives H1. This is S, that gives H2. And VW are also at the same positions as H's, so there. So let's see, 10 centimeters. I think I'm a bit. Oh, sorry, not 10 centimeters, 10 millimeters. So yeah. Otherwise, they should be symmetric. Oh, come on. Let me copy, move that. Okay, so 10 millimeter. That would be this way exactly. So I wish I had a different color. So let's offset this a little. Okay. So this will make the distance from H1 to F1, distance from H2 to F2 exactly um, the same. I think if I do that, 10 centimeter, 10 centimeter, 10 millimeter, 10 millimeter. Let's see, to the right, the other one to the right. Let's read the numbers again. So R is to the right, S is also to the right. So right to left, right to right. So 140, then this is 150 from that point, and 10. Okay, sorry. I think 10 is not that close. Let's see, 10 should be here. That's like that. Okay. Yeah. Third time's the charm. Okay, so this is 150. This is also 150. All right, so this is almost like a thin lens, except that the center is kind of thick. So it really doesn't matter how you draw the diagram. It's going to look like probably a thin lens. So if you, I don't really have a lot of distance I can put. I want to put distance over here so that the image wouldn't be very big. I don't have enough space to draw the object image here because of the scales. So can I maybe shrink this down a little? Okay, I had to shrink this down a little. So if I have an object, let's place everything on a grid. Okay, if I have an object somewhere over here, like this, I can just do a parallel line, right? Parallel hitting the second in the second interface that's going to go this way, right? So that's, and then also going through this, gonna hit the first principal plane and become parallel. Oops. So that be the image, right? Thank you.